In this review video, I thought we'd go look at the Lecture 3 notes here and just somewhat quickly go through those guys. So the nature of data, a definition, at least practically speaking of. In the final exam, I'm not going to ask you to give a formal definition of these. That seems kind of silly. But it is important to know what, for instance, a data set is. You have done a lot with data sets at this point. In the beginning of class, you all needed, or I requested you to give me a data set so I could use them to create the problem sets. And each of the problem sets, those Excel sheets that come with it, those are all data sets. So data sets are just a collection of data that you will use in an analysis. Qualitative versus quantitative. So quantitative is about quantities. Your data are numeric. There's a real number associated with that. In contrast, qualitative is about quality. So it's a word, and a category, that kind of thing. So a quantitative result could be a change of -5, so 5 less than whatever it originally was, and a qualitative would just be less than. So there's clearly some parallels, both of them have a direction, but only the quantitative has a number. That's not to say that qualitative data are bad or anything. There are some things that can only be described qualitatively, such as emotions. So we have happy or sad. Uh, we can't, there's no inherent number for that. Things can get a little vague when you try and assign numbers to qualitative data, such as please rate your happiness on a scale from 1 to 5. Well, now we are trying to make our qualitative data, what is strictly a nominal level data, and we're trying to make it quantitative. So we're trying to bump it up to an ordinal level data, an ordered category. Does that work? Well, kind of. Generally, we would call it semi-qualitative. So it's not as good as a real number because it is, as we'll learn here, it is a little subjective as to where you rank your data. But at least it is a number, so you can do some number-based things like calculate a median. You couldn't do that with just happy or sad. Objective versus subjective. So as alluded to, objective really means that we can prove and or disprove something. And I don't have to make a judgment call on it. My personal feelings don't get involved, or neither do my personal experiences. And subjective, I'm having to pull from some sort of outside frame of reference. So I'm being something of a judge where my personal opinion not only matters, but it has to go into the input. So in ranking my feelings, that is subjective because they are my feelings, and my feelings may differ from somebody else's feelings in the way somebody else may rank their data or their feelings. Empirical versus theoretical. Empirical comes from observation. Theoretical comes from theory. This is perhaps best exemplified when we're talking about probabilities. So probabilities that are based on distributions, such as calculate the probability using a normal distribution or a t-distribution given a certain critical value. The fact that we are referring to a distribution requires us to access the theory about that distribution. There's a theory that creates normal curves and t-distributions. So those are all theoretical probabilities, for instance. And we can compare that with empirical, where it comes out of the data. So if we calculate a probability based on the number of times something happened out of a total number of opportunities, we still get a probability, but that is an empirical probability. It's coming straight out of the data. We don't have to access any particular theory to come up with that. A variable is the thing that data sets are made out of. It is the thing we're asking questions on, the things that we have data points about, or data points on. Predictor versus response variable. So as this said, we didn't really get into this until lecture number 13 in correlations and regressions. So the predictor is another name for our x variable, and our response variable is the y variable, also called the, I guess in older times, also called the independent variable and the dependent variable, but now people tend to use predictor in response. In a data set, we have variables, and those variables generally appear as columns in our data. So if you were ever asked to ever think you need to add a new variable to your data, really that means we're adding a new column to your data set. Third bullet point here, correlation does not imply causation. So this also didn't really appear until lecture 13 and correlation and regression. So if we were to draw an XY plot, X tends to go on the bottom, Y tends to go over here. Let's say our data made a very nice looking line. Thanks to lecture 13 and that, we now know how to calculate statistics on this. We can calculate a correlation coefficient R. We can calculate a coefficient of variation R squared. We can take R and calculate a p-value. That'll tell us, okay, it looks like there's a line there. Is there really a relationship? How much does X variation in X explain variation in Y? And how likely is it to get this kind of result if the true relationship was actually 0? So that is what those three things do for us. Now, even in the case where R is a really big number, and R squared is a really big number, and the p-value is a really small number. So all three of those metrics are saying this is a really good line and we didn't get it by chance. The statistics tell us that. What these statistics distinctly do not tell us is that the change in Y is caused by the change in X. So it tells us we have a correlation, that the change in Y is related to the change in X, at least mathematically, but it does not say the change in Y is specifically due to a change in X. Just because just because Y changes when X changes doesn't mean if we were to force a change in X, then we would also force a change in Y. There could be, well, for one, we could have these backwards, and perhaps our X is actually Y and Y is actually X. So we still have a relationship, but it's backwards from what we plotted. Alternatively, there may be a third variable. Maybe there's a Z variable that when Z goes up, X goes up, and Y goes up. So even though we're looking at X and Y, it's actually due to this other variable that we didn't even mention. So the take-home message here, and a really important one, is just because you get good lines that make it look like X is doing something to Y, that is a correlation. It does not imply X is actually doing something to Y. There's 4 levels of data, and that is talked about in a separate video, so we won't spend any time on that now. Continuous versus discrete data. So this was mentioned in one of the earlier problem sets. We really didn't touch on it since then, other than talking about whether or not a distribution was discrete or continuous. And really this came up first with the binomial and the Poisson distribution. So let's do a quick plot of a symmetrical binomial distribution. So here we have a plot. This counts as a histogram for the binomial, where each of these represent the probabilities, that's a probability on the y-axis, the probability of getting a certain number of events. So 0, 1, 2, 3, and 4 events in this case. So there's 4 times I'm attempting to do something, and there's a probability that it never happens, and a probability that happens 1, 2, 3, or 4 times out of the 4 times I'm trying. I cannot, for instance, get an event happening 1.5 times. I am fixed to these certain numbers 0, 1, 2, 3, 4. And if I have a fixed number of possible outcomes, sorry, not number, if I have a fixed value for my outcomes, 0, 1, 2, 3, 4, not 3.3 or 3.79, those fixed values means we're talking about discrete data or discrete outcomes. That is certainly the case for the binomial and the Poisson distribution. When we got a little more advanced and we wanted to calculate probabilities of things, then we shifted from this discrete distribution to one that looked kind of like that. Kind of like that. And specifically, it's the normal distribution. So when we want to do, for instance, a one sample test of proportions. And we had a slide on that. I don't know that we actually ended up solving questions on it. But when we do, or try and do a one sample test of proportions, the binomial equation, which is the way we should really solve it, gets really clumsy. So instead, we use an approximation of the binomial distribution, which is the normal distribution. There is a difference in there, and it's an important one from a math standpoint, not so important from an application standpoint, that the binomial distribution is discrete. We cannot get a 2.7. But when we have a continuous distribution, like the normal distribution, we actually can get a 2.7. So when it comes to the math, we have to account for that change from a discrete to a continuous distribution. If we have a lot of samples, then we tend not to have to worry about it so much. If we have fewer samples, it becomes more important. Again, we didn't really get into that, so it's not something that I plan on addressing in any great detail, hint, hint, on the final exam. I guess my take-home message there is remember that something that is discrete means there are only a fixed set of values the data can take on, and continuous can take on any data value. Be able to identify the level in discrete versus continuous for a data set. So again, the level will be addressed in a different lecture. Discrete versus continuous, we just talked about. Precision versus accuracy. So this is often presented using bow and arrows and, well, really targets. So we had something like this. Something that is accurate is close to the true value. Something that is precise has all the measurements next to each other, but it may not be by the true value. So we can have something that is accurate and precise but not accurate because it missed the target. Something that is accurate but not very precise. So the central tendency is in the right place, but there's a lot of dispersion, so it's not very precise. And then we can have things that are just way off. It is not accurate, it's not by the middle, and it is also not precise. That's really all I think I care about you guys knowing. Statistics deals with questions. It helps us control for precision questions. So statistics is all about addressing variability. And that's really a precision question. If we have an instrument calibration error, so our accuracy is off, statistics does not help us with that. It does help us with precision questions. The concept of confounding variables, again, it was presented in that one lecture and we really didn't touch it again, and I doubt it's actually going to be something on the final either. Confounding variables means we're looking for a relationship, but there could be something that we haven't measured that is actually controlling our data. So in the plot that I had made earlier, actually, of the x is here and y is here, and it looks like there's a relationship between x and y, but really it's because of z. That z could be a confounding variable. Often it's not meant in that kind of context. I think the example that I gave in class was the confounding variable. It looked at the relationship, I believe, between temperature and snow, or something kind of like that, on modes of travel. So there were lower numbers of pedestrians and cyclists when there was snow on the ground, I believe, or perhaps I'm making it up, but we can go with it. So let's say there was lower numbers of pedestrians and cyclists when there's snow on the ground. And that makes sense because it is more difficult to walk and ride a bike in the snow. However, it tends to snow when it is cold outside, at least relatively cold outside. So we could also hypothesize that, well, maybe there are fewer cyclists and pedestrians outside commuting when it is cold outside. And because cold and snow are correlated, there's a correlation between those two, if all we have are number of pedestrians and snow, we don't know for sure that it is actually the snow that is doing the problem or causing the impact, or whether or not it is temperature. So temperature in this case is our confounding variable. Confounding means it makes things more difficult for us. It confuses things. Uh, we haven't learned any techniques to deal with that, so we're just going to leave it at understanding that plotting x versus y, for instance, may not tell the whole story, and you need to consider what else may be at play. Lastly, we have the definition of a census and its implication for uncertainty. So all of our hypothesis tests are dealing with samples. The opposite of a sample, or opposite of sampling, is taking a census. So if we have access to the entire population, remember this is population in statistical terms, not necessarily a population of people. It could be a population of animals, a population of ice cream flavors, or whatever. It's just the whole group that we could possibly collect data from. If we have access to that entire population in statistical terms, then what we're doing is a census. Whatever math we do to it, if we take a proportion, if we take a mean, there is no uncertainty in a census because we have literally included everything. Generally, we do not have access to an entire population, people or otherwise. We can only take a sample of that. And then we use our statistical powers to make an inference about the population from the sample. So we take a small group and we want to say something about the whole, which we have not measured. When we do that sort of extrapolation, when we take our sample and we try and apply it to the whole world, we introduce uncertainty. And that is what statistics does for us. Again, to reiterate, a census does not, a true census, where we really did sample everything, does not have that uncertainty.